Hello, MAT223 students. Welcome to the course. In this video, we go over week one activities together. First, let's review this theorem that you have seen before. It's about a different situation that one linear system of equation can have. Let's say we have m by n system. That means m equations, n variables. The system either is inconsistent or it has no solution. This can only happen in the case that if you do a row operation, row reduction of augmented matrix in the RREF, you get a row looks like this. That is a row which all coefficients parts are 0 and the constant part is 1. So this is the only case that in the RREF you can have inconsistency. In other words, another way of expressing this property is that rank of coefficient matrix and rank of augmented matrix are two different numbers. In other words, rank of augmented matrix is one more than rank of coefficient matrix. That also means inconsistency. Okay, that's one case. The system is inconsistent, no solution. So these are the cases that the system is consistent. So we have solution. Either we have one unique solution or infinitely many solution. For a consistent system, number of parameters is the same as you see here, n minus rank. R is the rank. Note that in the consistent systems, rank can be considered as rank of coefficient matrix or rank of augmented matrix. These two are the same thing. So for consistent system. So this R is any of those ranks. N minus R is number of parameters. When n minus R is 0 or n equals R, you have 0 parameters. So you have solution with no parameter at all. That means you have unique solution. You have one solution. And if n is more than R, then that means you have solution with at least one parameter. That means you have infinitely many solutions. And that's the situation. So these are all possible cases. No solution, one unique solution, or infinitely many solution with some number of parameters, 1, 2, 3, and so on. Okay, then let's go over the first activity, which is more about geometric. This theorem and combination of linear system with geometric point of view, which is intersection of planes in R3. Okay, we want to fill tables like this, that system of equation, number of the solution and rank and a picture corresponds to this situation. So this is a solved sample. Let's, for example, look at this is a system. What is the dimensions of system? We have two equations, three unknowns. It's 2 by 3, the dimension. This is the solution, parametric solution. How do you get parametric solution? If you like, you can write augmented matrix of this, do row operations to find RREF. Then in the RREF, every column without leading one, you can assign a free parameter for those columns and then find the rest of variables in terms of free variables. And you get something like this. Let me give you a very important remark. While number of parameters is always the same, parametric solution it's not unique. So if you have, for example, if you think that that's the only correct answer, no, actually for any curve or any line or anything, there are infinitely different parameterization of it. So if you have at least one parameter, there are actually infinitely many parametric solutions that they look different, but they are parameterizing the same thing. So don't worry if, for example, you are doing a question and your parametric solution exactly does not match with the final answer or these kind of things. Maybe your answer is actually correct. It's another parameterization of the same thing. Okay, move on to the next thing, rank. using this theorem, one way to see rank is when you did augmented matrix row operations, RREF, see how many non-zero row or how many leading one you have in RREF. Another way is using this theorem. Since I look at the solution and I see one parameter and number of variables is free. According to that theorem, it's free minus 1, free number of columns n, number of variables n, and our rank is 1. Rank is r, let's say, and we have one parameter. That's number of parameters. According to that theorem, number of parameters is the same as n minus r, which is free minus r. But number of parameters, I see that it's one parameter. So from this, I can actually compute rank as 3 minus 1, which is 2. So rank is 2. So if you actually write down the augmented matrix, do the row operation to get RREF, you should see that you have two leading ones. And a picture is like two planes intersecting. This it's a line having one parameter. So intersect at a line. So they have one common line intersection. So that was just a sample solution. Now let's do them for this. So this system, this equation system is given to us. The rest I need to find. Okay, so first let me solve this system. Uh, I want to do it as fast as possible. So if I can read the solution directly from these equations, I'll do that. But note that the general way to do that is to write augmented matrix, do row operations to get RREF, and then read the solution from it. Uh, I will skip that for this question because from this, while if you write it as a matrix like X, Y, Z, it's not in RREF, but still I can read a parametric solution from this. Again, parametric solution is not unique. If you do that process, you get another parametric solution. The parametric solution that I read, it's another thing. They are all correct answer as long as you did it correctly. So how can I read a parametric solution from this? I can see that from these I can find both y and z in terms of x. And that means a parametric solution. So solve this for y. You get y equals 1 minus x. Solve this for z. And you get z equals x minus 2. Am I right? Z equals x minus 2. Exactly. And now I see that x is a free parameter. Assign a name of a parameter, if you like, t to x. Then replace these x's with t. And you get this. It's a parametric solution where t is any real number. This is one correct parametric solution for that. If you do row operations and RREF, you get another set of parametric solutions. They are both correct. Okay, what about rank? Since I skip doing the RREF and row operations, I cannot read rank from that. If I have done that, I could read rank by leading number of leading ones. But that's no problem. That theorem, having a parametric solution, give me number of what is the rank of the matrix. So I know that number of parameter, how many parameter I have. Look at this. There is only one t. So number of parameter, according to that theorem, for a consistent system, it's n minus r, number of variables, rank. So it is number of variables, x, y, z, we have three variables. And rank is r. I don't know. That's the one that I want to find. So I find r, it's 3 minus 1, which is 2. So rank is 2. And finally, the picture, it's two planes that intersect at a line. So basically, you could say that it's the same as the previous picture. Or if you want to draw a new picture, let's say two planes that intersect at a line like here, like pages, 2 pages of a book. Then what about this? So I want to write down a system that this is the parametric solution and rank is 1 and finding a system and a picture for it. Okay, let me first see what do I have according to this theorem. So number of variables, it mentions at the beginning of all these questions that it's always in free variables x, y, z in R free. And you can see it also here. I have free variables and one parameter. So I have free variables n equals free and the number of parameters is 1. So according to that theorem, and I have solution, so it's consistent. According to that theorem that I showed you, the last part, n minus r or free minus r, where r is rank. Again, for a consistent system, rank of a coefficient matrix and augmented matrix are the same. So rank is rank of any of them. Equals number of parameters, which is 1. This give me that necessarily r should be 3 minus 1 or 2. But I want r to be 1. So these information and this information are not compatible with each other. And this is an impossible example. So this is impossible. And why it's impossible? I explained it here because if I have this as parametric solution, then this computation shows that rank should be 2. But I want rank 1 and this is not possible that have this as a parametric solution and at the same time rank 1. So this is impossible. So I cannot create any example for it. Let's move on to the next part. How about this? This is maybe the most straightforward one, I think, out of all. Uh, so I have a picture that suggests me that there is no solution because there is no common intersection. There is no point that it's on all three planes at the same time. So there is no intersection. From this, I see that no solution or no intersection, no solution to the system of equation or no intersection of three planes. But this says solution, I have exactly one solution. These two, again, are not compatible. This picture does not match with this set of solutions, this possibility. So this is impossible and I cannot create any system of equation and any example for it. And the last one, which is also straightforward, I have just one picture, which is three planes intersect. They look like intersect at one point. So now I see from the picture that I have only one solution. So let me create or write down a system of equation with exactly one solution. Of course, there are many, infinitely many correct answers. But let's write very simple one, the simplest things that we can have. The system of equation that give me exactly the unique solution that it has. Let's say x equals 1, y equals 2, z equals 3. That's a system of equation, and its solution is the same. It's x equals 1, y equals 2, and z equals 3. And it has only one unique solution. Now let's talk about rank. One way to do rank is to look at augmented matrix, then RREF, then how many leading one you have, and what is the rank. The other one, the other way to do it is using that theorem. I have how many solution and how many variable I have. I can read the rank from it. So I have three variables, n equals 3. Rank is unknown. And I know number of parameters is 0. I have one unique solution, so no parameter. That means 0 parameter. So number of parameter is 0. So that means n minus r is 0, or free minus r is 0, and this means r equals free. So the rank is free without writing the matrix. But just as extra practice, let me write down the augmented matrix of this. If the columns I assign is x, y, z for the variables, then the first equation is 1, 0, 0, 1. The second equation is 0, 1, 0, 2. The third equation is 0, 0, 1. Z, the coefficient of z is 1, and then 3. This it's already in RREF, and these three are leading ones. How many leading one or how many non-zero row I have in RREF? 3. So rank is 3. That's a second way to read the rank. Okay, now let's look at the another examples or activities which are true false. In this course, in tests and exams, you always have a question which has multiple parts, true false questions. So true false question are usually the most challenging parts of the course for students, because they need reasoning, they need proofs, they need arguments, mathematical arguments. They are not just computational. So let's, in this example, very simple true false question we have here. Let's just practice together. What is the general idea of doing a true false question? While it's very hard to give a general algorithm to do a true false question in general, but you can just have an idea of a general idea of what we should do. But you should, the best practice for true false question is to do a lot of them. And in our textbook, every section has one problem with multiple parts that is just true false questions. And I will give you also a long list of true false questions to practice. So make the best thing to get fluent in true false question is practice. But let me mention the general idea. When you see a true false question, make sure that you read the question first carefully, and digest it, completely understand it. Then think about what topic, what this question is talking about, this true false question is talking about, what claim it has, and try to find something in the course that you learned, definition, property of something, fact, theorem, proposition, something in the course that it's exactly related to this true false question. Make sure that you refresh your memory, or you review what was that theorem exactly saying, what was that definition was talking about exactly, and then compare it to the true false question. Try to use those things that you already know, there are true, properties, theorems, different things that you have in the course, or definitions. Try to change or manipulate them, play with them to get what you have in the true false question. If you are succeeded, you can do this, then basically you proved that the true false question is true, and you found a proof for it. By, for example, this theorem and these assumptions, I can do this operation and get this, and this is exactly what I want. Hence, it is true. And if you see a problem during this process, that you are doing a manipulation on theorems, definitions in the course to get what you have in the true false question, and you see that, oh, here they don't match with each other, there is a problem here, these are not the same. So not actually you see that, oh, then maybe this a statement is false, but actually you can create a counterexample for it to disprove it by making an example that exactly highlights this difference between the theorem or the definition or whatever you have in the course, and this claim and this statement, this true false statement. While this theorem says we should have this, but this statement claims something else. So make an example that shows this difference, and then you can create a counter example to disprove it. So general idea, these are the thinking process part. Don't include it in your solution. At the end, when you know it's true or false, and how you should create counterexample or how you should make a proof for it, then write down a clean, nice solution for the true false question. Let's do these questions. And always, when most of the time, when you want to prove something is true, you should prove it in general case. And when you want to show something is a statement is false, usually you disprove it by a counterexample. Okay, then let's do number 1. What does the question says first? Let me read it. It says if n more than 1 and the dimension of a consistent system is m by n, then I have infinitely many solutions. Think about this. This is talking about infinitely a linear system of equation, dimensions of it, being consistent or not, having infinitely many solutions. Where did I see all these in one place? The relationship between these kind of things. Exactly, if you even once you read the reading in the course, you see this connection. Oh, there was a theorem in the lesson that exactly was talking about these kind of things. Let me review it for myself. In the exam, of course, you don't have the theorem. You should have everything in your memory. But now let's look at the theorem. This theorem that I just saw. So we are talking about a consistent system, and I'm interested in infinitely many solutions. So basically, I'm focusing on this part of it. I have a system of equation m by n, and the system is consistent. I had these assumptions. Then my claim is that I have infinitely many solutions. Good. But what is the assumption or the condition that give me this claim that I have infinitely many solutions? It's that n is more than r. N was number of variables, r was rank. So let's go back there. Can I see that n is more than r in statement 1? Hence, I make a proof for it. What's given to me, what assumption I have is n more than m. M is number of rows, it's number of equations, and R is rank. Then this naturally, what I want is this. If I had this, I would be done. But I have actually this. Now this naturally asks me, what is the connection between these? How can I relate these to each other? So these are almost the same, except I have M here and R here. Then what is the relationship between M and R? R is rank, M is number of rows, number of equations. Do I see any relationship between them? Yes. If I look for it and think about is there any relation? Yes, there is an easy relation between R and M. So in the rank is number of non-zero rows in RREF, and M is the whole number of rows, the total number of rows. Of course, the total number of rows is more than or equal the rows that are not zero in RREF. So basically, I can explain why the other way. R is less than or equal M, or M is more than or equal R. Number of rows is more than or equal number of non-zero rows in RREF. So then having this, if I add this at the end of this inequality, I see that, oh, actually this also implies that n is more than r. And that's what that theorem needs to conclude infinitely many solutions. And then I see that, oh, actually this statement is true, and I found a proof for it. Let me write down the proof. Now that I know it's true and I found how should I prove it, I write it very nice and clear solution without those thinking process steps that I explained here. So I first say that clearly the statement is true. Mention this, that the readers understand. Oh, you are taking the path that this statement is true, and you are writing down a proof for it. To prove it, uh, first I need to assume that my assumptions. The assumptions are consistent system n by n and n more than n. So assume we have these assumptions. Assume that we have a linear system, n m by n system, and consistent. So we have a linear system which is consistent and with, what was the other assumption? N more than m. Okay, these are my assumptions. What is the claim that I want to prove is I have infinitely many solutions. So this, I understood that I should use that theorem to prove it. So to use that theorem, I need the condition that n is more than rank. But I don't have it here. So first, let me explain why m should be greater or equal than r, and then combine this assumption with this to get what I want. So first, let me focus on explaining why m is more than or equal r. Since m, or since R equals rank is number of non-zero rows in RREF, in the RREF of the augmented matrix, and M is the total number of rows in the augmented matrix, or let's just say total number of rows. We should have, or we have, total number of rows is more than or equals non-zero rows in RREF or R. Okay, then let me conclude that combining this and this, actually I have n more than R. So we have n more than m more than or equal R, or n more than R. Now it's time to use that theorem. In exams and tests, you don't need to memorize the number of the theorem number, but you need to mention that I'm using a theorem. I remember that I had a theorem in the course about this, and I'm using that. You need to mention by a theorem, hence by a theorem in the course. What I'm talking about is that theorem that I showed you, the last part. This system has infinitely being consistent and n being larger than that rank has infinitely many solutions. And that's what we wanted. That's basically the complete solution. But in that theorem, we had an extra information. Let me write it while I don't need it here. With how many parameters? With n minus R parameters. Again, this part can be completely deleted. I don't need that to prove that theorem, to prove this statement. This statement is only about having infinitely many solutions. So I'm good. So that's the solution for the first one. Now let's think about the second one. The second one, it's again talking about a m by n, 3 by 5 system, consistent system. And it's again about how many parameters involved. So if you think about it 1 second, you see that, oh, it's again about the same thing that we have seen. It's about the same theorem and even the same part that consistent system has n minus r parameters. So here we want two parameters. So number of parameters is n minus r, and it should be 2. But what is n? N is number of equations, a number of variables. It's 5 in this case. This is m by n. So it's 5. So 5 minus r. So if we have this case that we have two parameters, what we need according to that theorem is 2 to be 5 minus r. In other words, r to be 5 minus 2 equals 3. So basically, according to that theorem, if I want this statement to be true, I need necessarily rank to be free. Do I have anywhere in this statement that give me this information that rank is free? Let's look. No, I have this, but that's m. It's total number of rows. Basically, what the best thing I can say about rank is that rank is at most not free. So I can say that R is less than or equal free because free is the total number of rows. And rank is at less than or equal number of rows at the same also less than or equals number of columns. But now free is less than 5. So that's the best thing I can say about rank. R or rank is less than or equal free. But I need it to be exactly free for this statement to be true. So this suggests me actually this statement is not true in general. And not only it should be not true in general, so it's false in general. So what can not only that, but I found a counterexample. What is a counterexample for this proving this statement? It's any system with R less than 3 when R is not exactly free. If R is 2, 1, 0, whatever. As long as R, any system with these conditions, consistent being 3 by 5 system, but rank is not free, rank is 2, 1, 0. It's a counterexample for this statement. So let me write down the solution. To make this counterexample, you have a lot of options. As I said, any system 3 by 5 system to be consistent and having rank less than 3, it's good to go. But let's make simplest possible thing. What is the simplest rank that we can have? Rank 0. What is a matrix that has rank 0? The only matrix has rank 0, it's the 0 matrix. So basically, the simplest counterexample for this question to have rank less than 3, it's the matrix with rank 0 and the system of equation which has all the coefficients, all the constants, everything 0. That's the system of equation which is consistent and it has rank 0 which is less than 3, so it's a counterexample. Of course, this is not the only option. You have a lot more options, but this is the simplest one. Let me write down the solution. So I understood that the statement is false. It's not true in general. And to show this is, to disprove the statement for the general case, I may give a counterexample. Counterexample. I give an example with these assumptions, but not this not be true. So a counterexample is this system of equation, which it's, as I said, basically everything 0. Let me write it down. We have five variables. So it's 0, x1, 0, x2, 0, x3, 0, x4, plus 0, x5 equals 0. That's one equation, and we have three equations, 3 by 5 system. This is a 3 by 5 system. It is consistent. And how many parameters it has? So let me explain this. This is a 3 by 5 consistent system. To read how many parameter I have, I should talk about rank. Rank is 0. As the augmented matrix is the 0 matrix, augmented matrix is the 0 matrix, and it is in RREF, rank equals R equals 0. That means how many parameters we have. So by a theorem in the course, the one that we have seen multiple times and used it, so by a theorem in the course, this system has infinitely many solutions with how many parameters? Solutions with n minus r parameters. But n is 5, number of variables. R is 0 with 5 parameters. What I wanted was the system has exactly 2 parameters. This is not true. So the example that I provided, while have the assumptions, satisfy the assumptions, the conclusion is not true for it. So that is a counterexample for this statement, and that show disprove this statement and shows that this statement is not true in general, it's false. And that's the general idea to do the true false question. Again, let me mention very quickly. So first, try to read it and think about it, digest it completely and carefully, the statement. Then try to think about what information, definition, theorem, property in the course was related to this statement. Refresh your mind about that theorem definition and see the similarities and differences, and try to uh, change or manipulate that theorem definition step by step to get the statement that you have, the claim that you have. If you can do this, basically you proved it and it is true. If you cannot do it because in this process you see that, oh, actually these are different, this is the difference between this statement and this theorem, and when I change it. So not only you see that this statement should not be true, but you find a way to create a counterexample for this statement by creating an example that exactly highlights this difference between this statement, the true false statement, and that theorem or that definition or that whatever you have in the course. So you can create a counterexample to disprove this and show that it's false. So that's the general idea of true false question. But again, try to do many true false question, and that's the best practice to get fluent in them. Okay, that was the first video. Thank you for watching and have a great day.